Another method for determining the distance to stars, okay, other than parallax, is what we call spectroscopic parallax. Okay, so this can be applied to any main sequence star. Do not think of actual parallax. It's called this, but it doesn't use any parallax in doing it. Okay, so it can be applied to any main sequence star. And once again, does not involve actual parallax. All right. What it does, though, okay, is that it uses the spectrum and the peak wavelength we determine and calculate t. So use the peak wavelength. We find t from Vaughn's displacement law. Then we use the HR diagram, and we estimate the luminosity, right, based on where it might fall from the temperature on the main sequence. And then from that, we measure B, and from there, calculate the distance, okay? And the way that we can do that is given that B is just equal to the luminosity all over 4 pi d squared, all right? We can solve for D, which is the square root of L all over 4 times pi times B. All right, so we can do a few examples with this. We get a main sequence star. It radiates most of its energy at a peak wavelength of 2.4 times 10 negative 7 meters. Its apparent brightness is measured to be 4.3 times 10 negative 9 watts per meter squared. So the question is, how far away is that star? So, like I said, right into it here. Start with the peak wavelength. Okay, Vaughn's law can give this to us like this. And we see that the surface temperature is about 12,083 Kelvin. Okay, so the luminosity, right, they're saying is, let's see here. Oh yes, if we go to the, we have to go to the HR diagram. Okay, we go to the HR diagram, and at about 12,000, okay, we come up here. We see that it's approximately. I kind of drawn this a little off here, but yeah, we'll say 12,000 is approximately there. That we're given about 100 times the luminosity of our sun. We'll say. All right. So there we go. So it's 3.9 times 10 to the 28th watts, okay? And from here, we can just solve for B, plugging in for L and B. And when we do that, we get a distance of 8.5 times 10 to the 17th meters, okay? Approximately 90 light years, doing that conversion, approximately 28 parsec, okay? So that's pretty much the idea there for spectroscopic parallax. We could do the same thing here for Regulus, okay? We know the brightness, apparent brightness, and we have been given the luminosity, actually, so we don't even have to worry about using the HR diagram here. And we know that the distance from the Earth to the Sun, how they compare. So what this is looking for us here is actually, for us to do one of those fun IB ratios, all right? So actually, what this is looking at here is the ratio of the luminosities, right? L of the Sun over L of Regulus, right? We can say it's just equal to d squared Sun times the brightness of the Sun. This is, of course, getting rid of the 4 pi. Okay, so when we actually end up solving for the distance to Regulus, which is what they're asking us to do here, I'm going to skip through some of the math. It's just going to be the square root of the luminosity of Regulus all over the luminosity of our Sun times the ratios of their brightnesses, all right, times the distance to our Sun squared. So we actually have the ratio of their apparent brightnesses right here, and we have the ratio of the luminosities, and We know the distance from the Earth to the Sun, parsec right here, and we substitute all that in, we end up getting 25 parsecs. So this is just juggling around the luminosity definitions and ending up there. If you have trouble with how I got from these two places, well, from this equation to this one, you should be able to solve. And we just set up a ratio based on this right here, which, again, the brightness is equal to the luminosity all over 4 pi d squared. So if we solve for luminosity, it's just going to be b times 4 times pi times d squared, and those 4 pi's cancel out. All right? So that should help you out with that one. So that's pretty much it for spectroscopic parallax.